Welcome back, and today we're going to be continuing on with our calculations from experimental data and looking at how we calculate enthalpy and write thermochemical equations for that. So we've looked at calorimetry, so how we do simple experiments to get a measurement of the amount of energy that has been released into the system that the surroundings that we're measuring. So this is usually by measuring the change in temperature of the solution. And from that change in temperature, we said that we can calculate the amount of energy using the formula Q equals mc delta T, and that will give us an amount of energy that was given off from the particular system or taken in by the particular system that we're looking at, and then use the number of mole of substance that we were studying in order to determine the enthalpy. So we're going to take that now and turn that into a thermochemical equation, which completes the picture of an endothermic or exothermic chemical equation and allows us to write the most information. So thermochemical equations are essentially chemical equations that give the associated enthalpy value stated. So if you're ever asked to write a thermochemical equation for an experiment, it is a balanced chemical equation that includes the delta H value for that equation. And you must specify whether or not that delta H value is negative or positive, because remembering this gives us the idea of whether or not it is endothermic or exothermic. So we can see straight away by looking here that this is an endothermic reaction and this is an exothermic reaction. And then by looking at this, we can do a whole bunch of information and work out the amount of energy we get per mole, and whether or not, and therefore take it back through Q equals mc delta T and work out what the expected temperature change would be. So we can see here this is a standard combustion equation, the combustion of methane, which we would expect to be exothermic. All states are included. Okay, all states are included, and we have a fully balanced equation. And then this is the dissolution of ammonium nitrate, remembering that when we write the dissolution, we either add plus AQ to indicate that we're making it a solution, or the other way we can write this is to put H2O above the arrow, because the water is not actually reacting. It's just dissolving so that we end up with the dissociated ions, and we've seen that before. Okay, so this is the dissolution equation, and as we know that dissolution is usually an endothermic process because we need to put energy in to get those ions moving about the water. One thing that can be confusing about thermochemical equations is even though we write delta H as negative 802 kilojoules, and we should always include the per mole in this, it is per mole of the equation is one way to think about it. Because delta H is directly proportional to the molar amounts for our equations, if we end up with a coefficient of 2 in front of our fuel or the thing that is causing the energy change, then we need to actually multiply the delta H by that coefficient. Okay, so in this case, we're talking here about the combustion of 1 mole of methane to 2 moles of oxygen, producing 802 kilojoules of energy per mole. But if the equation was written as 2 lots of methane, then this would be multiplied by 2. Okay, so what we've done here is we've times the delta H by 2. Whatever happens to our equation must also help into our delta H value, and this again should be per mole. Let's have a look at a few examples. So using thermochemical equations, we can use the delta H value given and then work back using stoichiometry to work out how many mole of substance was around. We can answer all sorts of questions in terms of determining the amount of energy that's in food, how much ammonium nitrate do we need to put into an ice pack in order to make the temperature change effective enough for cooling. Okay, we can work out how much fuel is required to generate a certain amount of energy. So this is important for energy needs in society and things like that. So here we are back to our combustion of methane, okay? And this question asks us to calculate, so we know we're going to have to do some kind of calculation, and it wants us to work out the amount of energy. Okay, so remembering that amount of energy is given in kilojoules, and we have 500 centimeters cubed of methane gas. Well, first things first, we know that whenever we're dealing with gases, we need to convert into decimeters cubed, so we're going to have to divide this by 1,000. We're at STP, okay, so we know our temperature and pressure conditions, and then we're reacting in excess air, so we know that we have complete combustion. So these are all the things that we know before we even read the question, okay? And it is important to annotate your question so you know what you're dealing with. We've been given a chemical equation. We should check that it's balanced, and this one is, okay? And we've been given the delta H value because this is a thermochemical equation. So the first thing that we need to do to work out the amount of energy is to work out the amount of moles of methane, because we know we're going to have this much energy per mole. We can actually write this as an equation. Okay, so, sorry, let's work. If we know that delta H is equal to the energy per mole of substance, so now we can use this to rearrange. And we need to know, in order to find out the total amount of energy, we need to know the mole and the delta H. The delta H we have, mole we're going to need to use the information from our question. So if we work out the number of mole of methane, because we've got STP and a volume, we can use our molar volume equation, so N is equal to V on Vm. We were told that we have 500 centimeters cubed, which is 0.5 decimeters cubed, divided by Vm, which is 22.7, gives us 0.022 mole, remembering that this value is in the data book, in our constants page. So now we know we have 0.022 mole of methane. The next part of the question is to work out the amount of energy, and we can just take the number of mole and multiply by delta H to do that. The other way you can do it is to set up a mole ratio grid. We know that 1 mole of energy, methane will produce 840 kilojoules. We have 0.002 mole, and X is the one that we're looking for. Because the proportion stays the same as we have a set amount of energy per mole, we can cross-multiply and solve for X, which is the same value that we would get if we multiply 0.0223 by 840, which was our number of kilojoules from the thermochemical equation in the first place. Okay, so either way works. I think that you can also, if you remember this equation, it's not really a formal equation, but it certainly is. It's putting into an equation form the idea of what delta H is. So we can work out that the final energy released by the combustion of 500 centimeters cubed of methane is 19.9 kilojoules, remembering that delta H must always be in kilojoules. So pause the video and give this one a go, and then come back to watch the solution. So with this one, we're asked to determine the mass of propanol that must be burnt in excess air. So again, we know we've got complete combustion to produce 1.00 times 10 to the 4 kilojoules. So this is an energy value, okay, because of the kilojoules. Mass of propanol is going to be M. We don't have any other information, which means I'm probably going to have to get to this using this mole formula here. Okay, because I've been given a formula. This is propanol here. I've been given the formula of propanol. This is what is burning in air, even if I didn't know the formula for propanol. I've been given the formula of propanol, so I've got MR here. I'll want to work out M. So N I'm going to have to get from my delta H equation for energy. So here I've got delta H and I have energy. So now I can work out the number of mole. So from that, I'm going to get that the number of mole is equal to energy divided by delta H. which is going to be 1 times 10 to the 4, because it's kilojoules, so this is going to be 10,000 kilojoules, divided by, and this is where we need to pay attention, there is a 2 here, okay, which means this is the energy given off for 2 moles of propanol, okay. This one is per 1 mole, so what we're going to have to do is 4,034 divided by 2, okay, because we want it per 1 mole by definition. So we need to divide this one by 2 to get the per mole of propanol amount, and then that is going to give us a huge number of mole, 2017.02368. Okay, if we're looking at significant figures, then this is going to be 2.02 times 10 to the 3. Okay, so this is my number of mole at the moment. So now I have mole, I need to be able to calculate my mass. So the molar mass of propanol is going to be 60 grams per mole, because I worked that out before. So I have the number of mole, I have the molar mass, so mass is going to equal N times MR, which is going to be 2017 multiplied by 60, and we're going to get 121,021 grams, which is equal to 121 kilograms in our 3 significant figures. Okay, so these values can get quite large, especially when we're talking about energy for electricity or needs like that. Okay, the other type of question that we can look at is this one here, where we're told that ethane is used as a fuel in oxyacetylene torches. That's all just background. I don't need to know too much about that. Given that the complete combustion of 8.55 grams, so I've got a mass, produces 429 kilojoules of energy, that's my E, calculate the delta H for the equation. So delta H is going to be equal to my energy divided by the number of mole that was burnt. Okay, in this case, number of mole of ethane is going to be equal to 8.55 divided by my molar mass, which is 2426, which is going to equal 0.32885 mole. Okay, so now I have my number of mole. I need to divide the amount of energy by that. Okay, so delta H is going to equal 429 kilojoules, that's in the correct unit, divided by my number of mole, which is going to equal, type this into my calculator, 1304.546 kilojoules. Okay, thinking about our significant figures, we should have 3 sig figs, so 1.30 times 10 to the 3 kilojoules. And if we were asked to write the thermochemical, so because this is per mole, okay, so 1.30 times 10 to the 3 kilojoules per mole, we were asked for the equation, which means we're essentially writing a thermochemical equation. So delta H is equal to, we know it's going to be negative because we're burning fuel, so it's going to be hot, and we've got a 2 here, which means I need to multiply this value, the 1.3, by 2. Okay, so what we're going to get, okay, is 2.6 times 10 to the 3 kilojoules. as our final thermochemical equation, again because we're dealing with this coefficient. Okay, so that's the last example. We've walked through those. If they make sense, great, and we will do a bunch of practice on that. You should now be able to do up to page 224 in your textbook questions, and we will have some time to do that in class. I'll see you later. Bye.